The format of today's webinar is going to be slightly different than our earlier webinars since there is a lot of theory to cover as well as the implementation in our application. And so what we will be doing today is I will be speaking and covering some of the content and the theory. We have a series of slides, and once I cover the content in each slide, I will hand over to Uday, who will then demonstrate how we have implemented the contents of that slide within our application. So Uday and I today will be switching back and forth with me covering the content in the slides and Uday following up each slide with a demonstration. Please do feel free to ask any questions as we cover each topic in the slides, and we will be happy to answer all of your questions. So the agenda for today is an overview of feeds and speeds, and then we'll talk about setting feeds and speeds in tools and how you can create tools with the feeds and speeds, a tool library, save it and reuse it. And then we'll also be talking about loading feeds and speeds from the material table, and also finally how to use the feeds and speeds calculator. Okay, so having said that, let's go ahead and get started. In terms of feeds and speeds can be associated with either an operation or a tool. Now, each toolpath operation type has a feeds and speeds tab in the dialog. And this allows you the flexibility to design the feeds and speeds values which are specific to that operation. So that is how you would set feeds and speeds for a specific operation. And then in terms of feeds and speeds for a tool, in our mill and turn modules, you can also define the feeds and speeds for every specific tool that you have. And this allows the flexibility to have different tool definitions based on the type of material being cut. For example, wood, steel, or acrylic. So in summary, there are two methods. You can associate feeds and speeds with an operation, or you can associate feeds and speeds with a tool. And Uday will show you how this is implemented in our applications.
Thank you, Krish. Hello, folks. Good morning, good afternoon, good evening to all of you, and thank you for joining us for this webinar. As my colleague Krish pointed out, we'll be trying to make the webinar more interactive here as we are planning to switch between the slides and the application to kind of go through each and every aspect of it, what we're going to be covering in feeds and speeds today. Now, what we're going to be covering here is going to be applicable to all our CAM products, whether you're running Visual CAD-CAM, or you could be running our plugin for Rhino, which could be Rhino CAM, Visual CAM for SolidWorks, or even our Libre CAM product. So the content would be very similar depending on whatever CAM system you're going to be working with that you're currently using. So first I'm going to go ahead and talk about how we could set feeds and speeds for operations in here, and I currently have our Visual CAD-CAM application open, and I hope you're all able to see it. And as Krish pointed out, if you do have any questions during this webinar, you're welcome to post those questions and we'll try to get them answered for you. Now, to establish feeds and speeds in an operation, once you have a part designed or you have a part imported into your Visual CAD-CAM application, you could go into the machining operation type that you're looking to program. So in this particular example, I'm going to choose profiling as an operation in here. And you can establish your feeds and speeds in the Feeds and Speeds tab by selecting the Feeds and Speeds tab in the machining operation dialog. So each of the machining operations we have under 2, 3, 4, or even 5 axis has a tab for feeds and speeds where you can establish your spindle RPM. You can set the direction of your spindle. This could be clockwise rotation or counterclockwise rotations. This is typically output as an M3 or an MO3 for clockwise, or M4 or MO4 for counterclockwise rotations. And then you can establish your plunge, approach, engage feed rate, cut, retract, and departure. And I'm also going to go over what each of these parameters represent with an example here. Your entry motions make up the approach and engage feed rates, and then the exit motions make up the retract and the departure feed rates, and then your cut motions are part of the cut feed rates. Your plunge motion is the motion from your clearance plane down to your first cut level. And then the transfer motion is as you transfer from one cut location to the next, where you rapid from one location. It could be set to use rapid, which could be using your rapid feed rate that's defined in your machine tool, which is typically we output as a G0 for rapid, or you can use a set feed rate and you can specify a value for it, which will be output as a linear motion G1 along with the feed rate that you specify in here. So let's go ahead and take a look at how each of these parameters can be set in here. So I'm going to go ahead and define a tool. I'll just add a end mill, half an inch flat mill, specify the tool number. I'm going to hit save. And now as you go into this feeds and speeds tab over here, you can specify your spindle RPM for each operation. So this is one of the ways how we can specify it. And I'm going to enter in the feed rates in here. Manually, I'm entering it in for a plunge, approach, engage, cut, departure. I can also set the feed rate for transfer, or I can set the rapid feed rate that's used in the machine for rapid motions. I'm just going to set it to 100. Now these feed rate parameters that you're defining in here are also used for estimating your machining time as well. And we'll get to that at a later part of the webinar. I would then establish the other parameters for my cutting conditions, and I'm sure you're familiar with most of these parameters in here. We could establish your cut levels and all the additional parameters, and then the entry and exit. So we have the entry motions, we have the approach, engage, and then you have the retract motions as linear retract, and departure as part of exit. So as you generate the toolpath in here, you're noticing the different type of toolpath motions. The toolpath motion that appears right here in yellow is your plunge motion, and your plunge feed rate is applied right in here. So whatever you specified for your plunge feed rate under the feeds and speeds is applied for the plunge motion. And then you have your engage feed rate. So the engage, you have your approach feed rate and then the engage feed rate. So the approach and the engage are part of your entry motion. So it's set to lines and arcs in this example. So you can see that the approach motion is defined as quarter inch, and it's set to be tangent, and the engage motion is set to be radial in this particular operation. So if you choose engage motion to be radial or linear, and you go back and generate the toolpath, it's going to be applying the feed rate that you specified for your engage motion, and it's followed by your cutting motion, which applies the cut feed rate that you specified. And then finally you have your retract and the departure feed rates, which are part of the exit parameters under your entry and exit tab. So you can find each of these parameters, and the corresponding feed rates that you have defined or specified in here would be applied for the feed rate motion. So you could establish your feeds and speeds for each operation for each operation level. So you could be programming one or more profiling operation, and each operation could have a different setting for your feeds and speeds. So this is one of the ways how you could specify feeds and speeds in each operation. Now we also have some...
I just want to break in here. This might be a good time to show how we can customize the colors of these motions.
Sure, I'll certainly do that, Joe. Thank you. So by default, the colors for each of these toolpath motions, the plunge, approach, engage, cut, retract, and departure are represented using these standard colors in here, but you can go back and change those or customize them by going over to Preferences and selecting colors. In the Preferences dialog, you have color, and you can specify the color. You can see that the plunge motion color can be changed. You can just click on it and pick a different color from the color palette, or you can even go to more colors, and you can use standard or from the custom colors. So you can pick a color for these, and this will retain those settings what you specify. So likewise, you can specify the colors for the approach motion, the engage, retract, departure, rapids, and also arcs. Now you'll notice that in this particular example here, the the retract motion is appearing in a arc, it's a dark blue color because the retract motion happens to be an arc, so it's using the color that's assigned for the cut arc motions. So if you had used a retract motion that was output as a linear, then you would be seeing the colors that are specified in here. So you can use and customize these colors for the cut motion, the plunge, the approach, engage, retract, and departure. And as you make a change to any of these parameters in here, so if I go back to entry and exit, change the retract motion type from radial to linear and generate it, you will now notice that the retract and the departure motion colors are now updated based on what is set in here in your color preferences under CAM preferences. And each of these can be customized, and you can save those settings, so those will be retained and you'll have the same settings on other files that you're working with. Now, post-processing these operations will output the corresponding feed rates that you specified. So I'm going to go ahead and do a post, and you'll notice that your plunge feed rate, which I put in, was 10 inches per minute. Your approach, 15. You have your engage feed rate of 20, the cut feed rate right in here, and then you'll see your retract and the departure feed rates, and you're seeing the G0 motions for all your transfers or rapids being output as rapid feed rate, rapid motion. So there's no feed rate output on a rapid motion if you're using use rapid for transfers. Now the next thing I'm going to talk about here is how we can specify feeds and speeds to a tool. And we'll use the same example in here. So I could go into the tool tab, which is located under the machining objects browser, and you can create a new tool or you can edit an existing tool. Now, if you're not able to locate the Tools tab or the Machining Objects browser, make sure you click on Tools and Machining Objects, and that'll toggle the visibility on of the Tools and Machining Objects browser. You could select a tool, and as you go over to the tool type in here, you can select the tool type, and you have over on the right side, you have two tabs. You have the Properties, where you can assign your tool properties like your tool number, your number of flutes, your material, for the tool, and then you have a tab for feeds and speeds. So you could specify your feeds and speeds right in here, where you can enter in your spindle RPM. So I could specify the spindle RPM, specify the plunge feed rate, and also specify the parameters for the transfer feeds. And as I select Save Edits to Tool, since I'm modifying an existing tool, I'm going to Save Edits to Tool. Now the feeds and speeds are saved with this particular tool in here. As you program a machining operation, rather than having to go through the process of specifying the feeds and speeds over here manually, you could choose to load from the tool. And the feeds and speeds that you specified on the tool are automatically loaded in here. So you can specify the feeds and speeds for each of the tools that you have defined, and those can be loaded in automatically into an operation. Now we have what's called preferences for feeds and speeds. And you have these settings for the preferences, and by default it's set to load the feeds and speeds. When you program a new operation, the feeds and speeds are automatically set to be loaded from a tool. So what this means is, as you create a new machining operation, so let's say I want to program a chamfer operation, and I go in to create a new tool for a chamfer operation. I'm going to specify a chamfer taper angle. And as I specify the feeds and speeds for this and save it out in here, so when I go ahead and program a new operation, the feeds and speeds will be automatically, as you can see here, will be loaded from the tool. And that's the default setting which you will find under Preferences, CAM Preferences, and feeds and speeds. So automatically it's set to fetch the feeds and speeds values of parameters that you specify based on a tool. We can also choose to have it compute the feeds and speeds based on a feeds and speeds file, or use the last used default settings for feeds and speeds. So if you had an operation program with a certain settings, it'll use the same settings for the subsequent operations you program. You also have the ability to automatically use a percentage of the cut feed rate for plunge, approach, engage, retract, departure, and transfer feed rates. And we'll get into these details as we talk about in a couple of slides down, where we talk about how we can establish feeds and speeds based off a table file. And I'm going to go ahead and hand this back to Chris, who is going to cover one of the other slides, and we'll talk about those topics as well.
Well, one of the questions, there was a question regarding which takes priority, whether the operation feeds and speeds or the tool feeds and speeds. So let me explain that while it's switching to Chris here. It's always the operation feed rates that you see in the tab, the feeds and speeds tab of the operation, is what the operation will always use. The settings that you use in the dialog are just to load the feeds and speeds into the operation. So when you select load from tool, the settings will be automatically imported into the dialog here. And the operation at the end of the day is going to use what's seen in this tab. So in these feeds and speeds are going to be archived with the operation, and that's what it's going to use. I hope that's clear. Thank you, Uday.
Thank you, Joe.
Thank you, Uday. So the next topic we'll cover in this slide is in terms of how you can create a tool library and archive it along with the feeds and speeds that you associate with the tools. So in terms of creating a tool library, when you install the application, a tool library is pre-installed for you with a set of tools. And this is a good starting point for you to then customize and create your own tool library with the feeds and speeds that are relevant to your operation, to your environment. And so you can start with the pre-installed tool libraries if you wish, and then you can essentially create your own custom tool library based on that. So we just provide you a good starting point. You can then reuse your tool library so that all the feeds and speeds that you customize and specified will automatically be applied, and so that you don't have to keep redefining your feeds and speeds every time you start something new. And you can also have your tool library loaded automatically every time a part is created. So once again, the main goal here is to allow you to define everything once and reuse it as much as possible. And in this particular case, in this slide, we're talking about how to do that by creating your own custom tool library. And Uday will walk you through some examples now.
Thank you, Krish. So folks, will now talk about how we'll be able to make use of the make use of the pre-installed tool libraries in our CAM application, and then how we could customize it to be suitable for your machining needs depending on the type of material that you're going to be working with. So I'm going to go ahead and give you a quick example of how to do this in here. So what we'll be doing is we're going to go over to the Tools tab under the Machining Objects browser, and then I'm going to go under the Options under the Tools tab, and one of the options you'll find here is called Load Tool Library. Now there's going to be two libraries that are pre-installed with the application. We have a tool library for inch units. It's called Default English Tool Library, and we have one for metric units. Now this could be used as a starting point, a reference point for you to build your own library of tools. Now these tool libraries are saved under the data folder. So depending on whether you're running Visual Cam, Rhino Cam, Visual Cam for SolidWorks, or a Libre Cam, you can browse to the program data folder, and then under program data you'll see a folder called Microsoft Corporation. And under Microsoft Corporation, you can either navigate to RhinoCam, VisualCam for SolidWorks, or a LibreCam, and then go into the data folder. Now, typically on a Windows operating system, the program data folder may not be set to be visible automatically. So in order to make it visible, you could go into your control panel, whether you're running Windows 7, 8, 8.1, or 10, and go under Appearance and Personalization, and you can go under File Explorer options where you have this option called Show Hidden Files and Folders. Select this, and then there's this option called Show Hidden Files, Folders, and Drives. You can select this. An easier way to find this is just type in Show Hidden in the search control panel, or you can even do a search in the Windows start menu for search programs where it'll find you, it'll navigate to the location. So once you made this visible, you'll be able to easily access it, and by default, when you run the application, VisualCam will be pointing you to the data folder. Even though the files and folders could be hidden, you still will be able to access it. So you can just select the default English tool. Since I'm working in inch units, I'm going to be loading the default English tool in here, and I'm going to pick open. And as you can see, there's a list of over 56 different tools in here. And as you go over to these tool tab, I'm going to just place them on the side here so you can get a better view of all the tools in here. And you can edit each of these tools. As you double click on it, this will basically show you the type of tool. What's defined, this is an end mill, a flat mill. We have tools defined under each tool type, ball mills, corner radius tools, tools for engraving. So you can see that there's different tool types defined in here. And as you select each of these tools, you can assign your tool numbers, and you can go ahead and assign your feet and speeds for it. So you can specify the feet and speeds that you'd like to use, and then click on Save Edits to Tool, and that'll save those edits to the tool. Now once you establish these tools, you could save them to a library. So to save tools to a library, you just go ahead and select Save Tool Library, and you can specify a name for it. And if you'd like to save it in a default location, which is the data folder, it's going to point you to this default location in here. And you could call it based on the material you're working with. If you have different types of material you're working with and you would like to use different tool libraries, I can call this tools for cutting aluminum or tools for cutting steel. And you can name them by either the material type, or if you have different types of CNC machines you're working with, you can have tool libraries named based on the machine tool type, and you can save all of those tools with the library. Now, if you'd like to build your own custom library, you could do that as well. If you prefer to use your own, start from scratch by creating your own tools, you could choose to unload the tool library, and then you can start defining your own tools in here, where you can specify a name for the tool. You can specify the properties. So I could start with, call it a flat mill 1/2 inch. Specify the properties for the tool, assign the tool number, and as I go over to the Feeds and Speeds tab, I could specify the feeds and speeds right in here and enter in. Now we'll talk about how we can use the load from file option in a couple of slides down the road. But you can specify if you'd like to manually enter in your plunge, approach, engage, cut, and retract feed rates. You can specify these parameters and select Save as New Tool. So you can define tools under each tool type in here. I'm going to call this ball mill 1/4 inch. Specify the tool properties. Set the feeds and speeds for each of the tool. Save as New Tool. So once I have these tools saved, I'm going to save them to a library in here, and I can specify a library to be saved under. And once you save it to a library, the last saved tool library or the last loaded tool library can be automatically loaded. So if you're working off of a different project in here, different part, you can select the tool library that you wish to load, and the tool library is loaded. Now when I go ahead and create a new part, you will notice that the last loaded tool library is automatically loaded. So this saves you the time in having to go back and look for the tool library to load. So, and this is done automatically for you. And there's a setting for this under CAM Preferences and under Cutting Tools. So if you go to CAM Preferences from the machining browser and then select Cutting Tools, you'll see that by default it is set to always load the last loaded tool library on the startup, which means each time you run the application or you open up a new part and you're working in the same units as you did before, it'll load the last loaded tool library. It also points to the folder where your last loaded tool library is located. So automatically it loads it. When you close the application, restart it, it's loading. And the beauty of this is once you have the tool library loaded, it has all your properties for the tool that you specified and your feeds and speeds. So now when you create a new machining operation, it's automatically going to load the feeds and speeds that you defined on the tool. So this saves you a significant amount of time having to rekey each of these parameters as you program machining operations in here. So you could take advantage of defining your tools, establish your feeds and speeds, save them to a library, and loading the library will automatically reload the same library as you create new programs for different types of parts in here. So folks, if you do have any questions, you're welcome to post those questions in the questions panel and we'll try to get them answered for you. So I'm going to go ahead and switch this back to Krish and he will cover a few additional topics for you.
Thank you, Uday. So the next topic we'll cover is feeds and speeds in terms of defining and reusing feeds and speeds based on operations. Now, after you install the system and you start using the system, essentially you can create your own default knowledge base for feeds and speeds and other parameters that are associated with operations. So that when new operation is created, the feeds and speeds and the other parameters that you saved as a default for that particular operation will be loaded from the knowledge base. Uday will walk you through an example of this, but for example, if you were to take the profiling operation and you were to go ahead and set and define your feeds and speeds and the other parameters associated with that operation, and you save that as the default, the system will then use that as the default the next time you use that same operation. And Uday will walk you through this as well. Now, you can also create a custom knowledge base where you can take a set of operations and load those to a knowledge base. So these are operations that you would commonly be using, and you define these operations once, you define the parameters, including the feeds and speeds, and you store it in a knowledge base. And you can then reuse this knowledge base in your next project, and all the operations and the parameters and the feeds and speeds that were archived will now be available to you. So once again, this saves you a significant amount of time in being able to define, archive, and reuse. And Uday will walk you through some examples now.
Just to make clear, I just want to make this point, Krish, that what we are describing here are different ways of skinning the cat, I guess, if you will. So there's not a single way that you can customize your feeds and speeds for particular operations. So I just wanted to make that clear. We're not showing something that's sequential. It's just different ways. You may choose to use a tool library for saving feeds and speeds and then loading it to the operations. That might be your preference. Or you could use knowledge bases for saving your feeds and speeds. So different ways of doing the same thing. It really is up to you. Thank you, Krish.
Thank you, Joe.
How we'll be able to use the default knowledge base to save the feeds and speeds. So those settings can be automatically be reused in addition to other parameters that are loaded from the default knowledge base. Now, as you can see on this particular example here, we have a profiling.
I'm sorry to break in. I think we lost the first part of your whatever you're saying. So just if you can repeat what you were saying, that'll be good.
Okay, sure, will do. So as Krish pointed out in the slide, where we're going to take advantage of how we could save the parameters, feeds and speeds and other cut parameters to a default knowledge base and reutilize the default knowledge base on new operations that you'd be programming on other parts, and we're going to demonstrate that in here. So what we currently have is we have a profiling operation program. You may have noticed this, how we program this profiling operation we were demonstrating during one of the earlier topics. So I have established the feeds and speeds for this based on the tool. So I used one of the techniques to load from tool to load the feeds and speeds that was defined for this half-an-inch end mill. And we've generated a profiling operation in here. Now, once this operation has been generated, I could save the operation parameters, including the feeds and speeds parameter and any additional parameters that you may have set. Here I have it set to direction as climb, determine the cut side using a 3D model. I may have some additional parameters specified like arc fitting and maybe even sorting when adding multiple profiles. All of these parameters I've set can be saved to a default knowledge base, a default. So you can right-click on the operation and you can choose Save as Defaults. So when you select Save as Defaults, it'll prompt you with a dialog to save this under the Defaults folder. I'm going to give it a name and then hit Save. You can choose the Defaults folder or you can pick a folder of your choice. So once you save this to a defaults file, it'll automatically notify you that the operation is saved to a default. And the next time you program a new operation of the same type, in this case it happens to be a profile, you will notice that the parameters, including the feeds and speeds, are being loaded from the defaults that you had saved, so you don't have to go through the process of re-establishing your feeds and speeds. Now, in addition to the feeds and speeds, all the other parameters are also being loaded from the defaults. Now, these could include your cutting parameters, where we had already the cut direction set, your cut start side set, even your depths, like where you specify the cut levels, your entry and exit parameters, advanced cutting parameters. So all of these are being loaded from the defaults. Now, you can have a default setting for each and every operation type. So for example, if I have to program a hole machining operation in here, so I could do a drill operation, I can select all of the holes on this flat face. I can pick a drill tool. I can specify the feeds and speeds here to be loaded from the tool, establish the other parameters, the type of drilling, the depth, drill depth. All of these parameters can be set, and I can generate the toolpath and go back and save it to the same defaults. So when I click Save as Defaults, the defaults knowledge base will now have the default settings for both these operation types. So when you are programming another drilling operation on the same file or on any other part, by selecting the drill operation from the machining operations menu in here, you will notice that the feeds and speed settings are being loaded automatically from the defaults. And all of your other, in addition to all of the other cut parameters, as you notice here, these options are automatically selected, so you don't have to go through the process of resetting each of these parameters, which is a very nice productivity feature, and it saves you significant amount of time having to go back and reset the same parameters over and over again on each of the parts you're programming. Now, you might be wondering, where are these settings saved for the defaults? So if you go back into CAM preferences and you go over to machining, you will notice that under the group called default parameters, it's set to use the default knowledge base. So it's set to use the default knowledge base one we create. So it automatically assigns the last created default knowledge base to load. Now you can have one or more default knowledge bases defined. Now this could be defined based on the type of materials you're working with, or maybe it could be, you could classify them based on different categories. Could be based on the type of machines you're using. If you have one or more machines, you can have a default settings for each machine. Now to switch back to the system default settings, you just click on the pull-down menu in here and go back and change it to undefined. And as you create a new operation and right-click and select Save as Defaults, you'll be prompted to specify a name. So before programming a new machining operation, you can choose which default knowledge base to use by going into CAM Preferences and Machining, and you can make the selection in here for the default knowledge base to use. So this is how we can establish a default knowledge base, and by creating a default knowledge base, your feeds and speeds and all the other cut parameters would be automatically loaded from the default knowledge base when you program a new operation by selecting the operation from the machining methods and the group called machining operations. Now there's one other topic Krish covered in the slide where we can create your own knowledge base of operations. So the creating a knowledge base of operations where is like archiving your workflow or entire sequence of operations to a knowledge base. And this can be done by going into the program tab. You would go to the group called knowledge bases and select save to KB, or save to KB represents saving to a knowledge base. I'm going to select save to KB. I can specify a location where I want to save it. You could be saving it under your data folder, or you could be saving it in any folder of your choice, and I'm going to select save. Now as I start programming a new operation or a new part, I could simply load the knowledge base by going into the knowledge bases group under machining operations and choose load knowledge base and select the knowledge base, and this will automatically load the operations that you had created in the knowledge base and saved it, and it includes all of the parameters including the feeds and speeds that you had defined in the operation. So you could have one or more profiling operations, and each profiling operation could be using different sets of feeds and speeds, could be using different set of tools, different set of parameters. So as you save and load them from a knowledge base, each of those operations that are loaded in the knowledge base will have the parameters that you had saved. So this allows you to reuse those operations and reuse those feeds and speeds without having to go back and manually edit them and modify them. Now if you need to change any of the parameters, you can always override it by going to any of these tabs. In this particular case, it happens to be feeds and speeds, as this is the topic we are focusing on today's webinar. So if you need to modify your spindle speed or any of these, you're always you have the ability to change it or modify it. So we talked about two things in here. One is a default knowledge base, and we also talked about how we could save these operations, one or more operations that you've created, into a knowledge base, which you can archive it and then reuse those knowledge base on other operations. And I'm going to go ahead and hand this back to Chris so he can cover a few more topics for you.
Thank you, Uday. So the next topic we'll cover is how feeds and speeds are calculated. So this is the feeds and speeds calculator that's available in our system. In order to calculate feeds and speeds, there are a couple of things that are taken into consideration. The first is data from a table. And Uday mentioned this a little earlier when we were walking through some of the menus, and you saw load from file. And this is what the data from table is all about, and Uday will go into some more details. But the data from table essentially, based on the stock material and the tool material, feeds and speeds are calculated. And this information is stored in an external file, and Uday will show you where the external file is stored and how you can add your own materials to the tool. But this first piece of information to calculate feeds and speeds comes from this external file. The second set of parameters that need to be used for calculating feeds and speeds are the input variables in terms of the tool diameter and the number of flutes. And Uday walked through this as well when we were first talking about defining and creating your own tool library, and he'll cover that in a little bit more detail. So based on the tool diameter and the number of flutes, the system then uses all of these parameters combined to calculate a spindle speed, which is measured in RPM, and a cut feed, which is based on the units you're working in, whether it's inches or millimeters. So just to summarize this slide before Uday gets into the demonstration is, in order to calculate the feeds and speeds, we use the data from table, which is the materials file, and we use the input variables, which are the tool diameter and the number of flutes, and we therefore are able to create compute a spindle speed and a cut feed. Go ahead, Uday.
Thank you, Krish. So folks, we will now cover the topic on how we can establish feeds and speeds based on the material that you're going to be using for cutting this part, and how the feeds and speeds computation, the calculator that's built into the application, can be effectively used for it. Now, as you go through the workflow of defining your tools and establishing the workflow for machining the part, there's a material option in here where you can choose the material type that you're going to be using for programming this part. Now, as you select the material pull-down menu here, there's a standard list of materials that's by default included with the application. So you can choose the material type from this list, or if the material that you're looking to work with is not on the list, you can customize the list. We'll talk about that in a short moment. So in this particular example here, I'm going to pick the material as aluminum 6061, and this information is being read from a materials file, and I'll get into the details in just a moment. Now, as you define the material type, and as you go through the process of defining your tool, where you can specify the tool material type. So what we initially defined was the stock material type we're going to be cutting. Now, in this particular tool dialog, you're going to be defining the tool material type you're going to be working with. This could be carbide, it could be high-speed steel, or ceramic. So if you select the material type as high-speed steel, HSS, and then as you go over to the tab called Feeds and Speeds, now down at the bottom of the tab, there's an option called Load from File. Now, as you select Load from File, you will notice that the material that you chose for the stock material is automatically set as you define this in the material dialog, and the tool material type is also automatically set since you define under the Properties tab in your tool definition. Now, from the material file, it automatically has information of the surface speed for the stock material and the corresponding tool material, and the feed per tooth. And also there are certain input variables like your tool diameter, number of flutes. Those are the variables that are used in establishing the spindle speed and the cut feed rate. Now, the surface speed is defined as how fast the cutter periphery is traveling with respect to the workpiece. So you can use the suggested surface speed for the material that you're cutting to determine the spindle speed. And also you may want to keep this in mind, the larger the cutter, the bigger the surface speed will be. So our feeds and speeds calculator is using the information that you have for the surface speed and also the feed per tooth to establish the spindle RPM and the cut feed rate. Now, the feed per tooth is defined as how fast the tool itself is moving with respect to the workpiece. And this is a property of the cutter. And the higher the number of flutes you have, the faster would be your feed rate. So if you notice here, for the surface speed and the feed per tooth, and the diameter of the tool in this case happens to be 1/2 inch, and we established the number of flutes as 2 under the properties dialog, the spindle speed and the cut feed rate is computed. Now, these information that you see in the feeds and speeds dialog could be used as a good reference for you to establish the most ideal feeds and speeds for your machine. Now, you also may want to take into account your, the capabilities of your machine, depending on what is the maximum spindle RPM and the feed rates your machine can handle. You may also want to take that in account, but this can be used as a good reference as a starting point in here. Now, once you select OK to accept these parameters, you will notice that the spindle speed information is automatically transferred into the spindle value, and the cut feed rate is also transferred in here. And also the system automatically computes and applies a percentage of the cut feed rate for your plunge, approach, engage, retract, departure, and the transfer feed rates. Now, we'll show you where these defaults are set. We did talk about it a little briefly earlier during the webinar. As you go into CAM preferences and feeds and speeds, you will notice that the plunge feed rate is set to 50% of your cutting feed rate. So if your cut feed rate is computed as 24, the plunge feed rate uses 50% of that, which happens to be 12. The approach is set to 75. The engage is also set to 75, and then the retract, departure, and the transfer rates. Now, these percentage defaults can be changed, and you can change it based on what would be more appropriate, what would be more suitable for your machining needs. But these are the default settings in here, and you can use these settings, or you can change them to the preferred settings. Now, once you establish this and save the tool to a library, those information are automatically saved like we talked about earlier. So you can establish the feeds and speeds using load from file directly from the tool definition dialog and have it saved to a tool library. Or you could also go into a machining operation. You go into the feeds and speeds tab, and you can use the same load from file option in here as well to compute your feeds and speeds based on the stock material, your tool material, and you can compute the feeds and speeds from here as well. So the feeds and speeds, the load from file option for feeds and speeds can be accessed both from the tool definition dialog as well as from the feeds and speeds tab in any of the machining operations that you're working with. Now, there's one other nice feature I want to point out in here is rather than having to go through the process of computing the feeds and speeds from the file for each operation, you can choose to automatically compute it from the feeds and speeds file by selecting the default for new operations to use from the feeds and speeds file. So what this does is when you change the machining preferences to feeds and speeds file, as you create a new machining operation, and once you selected the tool, the feeds and speeds in here are automatically computed, so you don't have to go through the process of selecting the load from file and then selecting OK in here. It'll automatically populate the feeds and speeds from it automatically for you. So unless you want to go back and change it, you can always call upon the feeds and speeds file dialog, but selecting use the feeds and speeds file will automatically compute the spindle and the other feed rate parameters when programming new operations if you have selected it to use feed rates for new operation from the feeds and speeds file instead of the tool in here. Now I'm going to talk about the material file, where this is saved, the feeds and speeds, and to show you how you can customize it as well. Now I'm going to open up a Windows Explorer in here, and you'll notice that under Program Data, Microsoft Corporation, you pick your corresponding CAM product. This could be Visual CAD CAM. You could be using RhinoCam, Visual Cam for SolidWorks, or even Alibre Cam. So you go into the folder, and there's a folder in there called Materials. So you open up the Materials folder, and you'll notice that there are texture map files for several different material types, and also there's 2 XML files in here. There's one for inch units, and there's one for millimeter units. Now, you can edit these XML files using any text editor of your choice. I'm just going to pick Notepad in here, and you'll notice that the information that's contained in this XML file is what's automatically being populated into the load from file. So you'll notice that for material type aluminum, if you're working with 2024 or 6061, for example, you'll notice that the type of operation is milling, and the tool type here is defined as carbide, and the surface speed in here, which is defined in feet per minute. So it's set in this particular material file, and the feet per tooth, which is the property of the cutter, which is also defined here in IPT. So this information that you specify in the material file is also, as you can see when you go to your tool definition in here and go to load from file, this information for the surface speed and the feet per tooth is populated from this particular file. So in this particular case, I've chosen the material to be, the tool material to be high-speed steel, and you're seeing that the information for the high-speed steel is this is where it's being read from. Now, if you need to modify or change it, you can modify the default XML file, or you can also have one or more XML files saved in the same folder under the materials folder, and you can choose which material file to use for computation of your feeds and speeds. You can also add additional material types, or you can delete material types that are in the list. So if you're working with different types of wood, you can have one for each type, or one for oak, mahogany, different material types you can customize. You just need to make sure that you maintain the same format and also use the same type of tags in here as you see for each material type, with the opening and closing tags for material and the names. And if you also have a texture file for, you can assign it the texture file, you can use the bitmap file to map to it. So this is the format in which the material file is defined, and you can have one or more of these material types defined, and we can use them, we can pick which material file to use. So if you go back into this folder, let me go ahead and make a copy of this in here, and I made a copy of this folder file, and I'm going to call this file number 2 or 3, whatever you want to name it. And as you change the name for it and you go back into the application, you go back to the materials dialog, right in here you have a drop-down menu to choose which material file to use for computation of your feeds and speeds. So you can have one or more defined, and you can customize each of these material files to your machining needs, the type of materials that you're going to be working with. So once you have the material file set, when you compute your feeds and speeds, it's going to use that information when you pick load from file. It's going to read that information from the material file to establish your feeds and speeds. Now, folks, if you do have any questions, you're welcome to post them in the questions panel. I'm going to hand this back to Chris, so he's going to give you some more additional information about the feeds and speeds.
Uday, before you do that, could you just bring up the calculator and hit the help button and to bring up the online help?
Certainly, Joe. So I have the feeds and speeds tab. I'm going to pull in the calculator and select help. And this is how we can access the online help for the feeds and speeds load from file dialog.
Thank you, Uday. I was just looking to see if we have the data format for the table in the online help somewhere. There was a question about that.
I believe we do have it documented, and it should be under one of the topics. I can try to look for it. And
okay, we don't need to do that right now. We can send it out by an email once we have that. So, and also I just put up that blog article on how to customize this material file. So that's also a very good resource if you're interested in doing that. Thanks, Uday.
Thank you, Joe.
All right, thank you, Joe, and thanks, Uday, as well. So this slide is just essentially a a summary of what Uday covered in terms of the formula that's used for calculating the spindle speed and the cut feed rate. And as Joe mentioned, you will also find more information about this in the blog article. So I won't spend a lot of time going through this slide, but just wanted to show you what the formula is for calculating spindle speed and the cut feed. And this information is also available in the blog. And the next slide is our final slide for today. In this, we will cover how the speeds and speeds are calculated for 4 and 5 axis toolpaths. And in order to compute the feed rate for 4 and 5 axis toolpath, we first figure out the distance traveled by the tool, and then the time taken for the traversing move, and then using these two, we compute the time for travel as the distance divided by the feed rate, and then the inverse time feed rate is 1 over the time for travel. Now, I know that I simply read through these bullet points on the slide, but it'll make more sense for you when Uday walks you through a calculation. But we just wanted to give you the background before Uday brings up a calculator spreadsheet and shows you how this is done. Go ahead, Uday.
Thank you, Krish. So folks, there's two things we're going to talk about. As Krish pointed out in the earlier slide, we'll show you how our feeds and speeds are computed when we use load from file. We'll talk about how it's done in using the calculator in here. And then we'll also show you how we use feeds and speeds for our multi-axis motions in here as well. So I'm going to give you a quick run through of both of these in here for the feeds and speeds. So what I'm going to do here is I'm going to bring in a spreadsheet for you folks so you can take a look at it. And also we'll basically based on how the calculations are done. So as Krish pointed out, for computing the spindle RPM, we use the surface speed in inches per minute, and in the denominator we're going to use pi times the tool diameter. These are the variables in here. Now the surface speed in the XML file or the materials file, you're going to be defining it in feet per minute. So if you're working in inch units, it's in feet per minute, so we automatically take that times 12. And then in the denominator you have the value of pi times the tool diameter. So if you actually specify your surface speed and the tool diameter, your computed spindle RPM is 3,055 RPM for a half an inch tool with a surface speed of 400, and that's exactly Also, what you're seeing over here, if you specify the same parameters for the feed per tooth and the surface speed, you're seeing that you're getting a spindle RPM of 3,055 and a cut speed of 61, exactly what I showed you here in the spreadsheet as well. So I'm going to put this over on the side here so you can actually see them, compare them side by side right there. So that's the exact value what you're seeing here in these two dialogues as you see it. So the surface speed, the spindle speed is computed using this math right here. Now, how do we compute the feed rate? So we take the variables, the feed per tooth. Now, this is your feed per tooth is basically set, it's being read from your feeds and speeds file, which is the property of your cutter. And then we also take into account the number of flutes and times the spindle RPM that was computed. So the feed rate here is basically, if you have your spindle RPM as 3,055, your feed per tooth is 0.01, and then the number of flutes is 2, your computed feed rate is going to be 61, and that's exactly what you're seeing here in the calculator. So I just wanted to show you what is the math behind it and how our feeds and speeds calculator computes these parameters, and you can use this as a reference, or you can come up with your own you know, if you have a if you want to use your own way of computing, you can always feed those parameters in here, and then you can also have the XML file, the feeds and speeds file, updated to your application needs. Now, this is how we use it for 2- and 3-axis operations, and also if you're using multi-axis operations and not programming inverse time feed rate, we use the same calculator in here as well for programming multi-axis as well. But if your machines can handle inverse time feed rates like G94 or G93 to toggle on an inverse time feed rate, and the G94 to toggle off the inverse time feed rate in here, we could be using you know, inverse time feed rates to be able to program feed rates for 4-axis, and for that I'm going to give you a quick example in here as well and how that is done. So as Krish gave you the math that's behind the computation of inverse time feed rate in here, I'm going to show you with an example of how the inverse time feed rate is computed and how it's done in the post processor. So in your post processor, depending on the type of post processor you're working with, or machine tool you're working with, you would want to go under the feed rate section, and you would want to select the option to output inverse time feed rates. And then typically for the inverse time feed rate, the code to toggle it on is a G93, and the code to toggle it off is a G94. So as you specify the G93 and G94 options in here, the system will now use the inverse time feed rate math, the computation, to compute the feed rates for multi-axis motion, and this is applicable to both 4- and 5-axis continuous operations. They're not applicable to indexed operations, only continuous or simultaneous 4- and 5-axis operations. So you will see a feed rate value that's being computed and output for each of the lines of the code in your posted output file. So you can toggle it on by going into the inverse time feed rate option, and this is available in Expert, Pro, and Premium configurations. Now all the other options we talked about are available right from standard configuration of our products as well. Now while we're on the post processor page, I wanted to talk about a few other things in here. This is where you can also specify your high values and the low values for your feed rates, depending on what is the lowest feed rate you'd want to set, and the high value is the highest value that your machine can handle for your feed rates. So what this means is if your program feed rate is higher than the high value that is set in the post processor, then the posted output will be capped to the high value that's defined in the post processor. So for example, if your program feed rate is 325 inches per minute and the high value in the post is set to 300, your posted output will show a feed rate of 300 and not 325. So that's what the high and the low values are, you know, they use to basically set the highest feed rate and the lowest feed rate values, the range for your machine tool. Now, certain machine tools expect the feed rates to be in units per second. This could be in inches per second or inches, millimeters per second. So in your machining operations, you would be establishing your feed rates as units per minute. It could be inches per minute or inches per second. Now over here, you have the option called scale factor, where you can scale the output to units per second. So if you put in a value of 0.016667, which is basically scaling it from per minute to per second, the posted output will be reflected with the change. Now, one of the machine tools that I'm familiar with that uses units per second is multicam. There are several other machine tools which also expect the feed rates to be in inches per second. So you do that scaling in the post processor. However, when you're programming the toolpaths, you're still defining your feed rates in inches per minute, or if you're working in metric units, you'd be defining it in millimeters per minute. And the scale factor in here will take care of the conversion from your inches per minute to inches per second. And this is set right in here under the feed rate tab. Now, very similar to how we have the feed rates for the high and the low values, we also have a option for the spindle where you can set the high value and the low value depending on what your machine tool is capable of. So certain machine tools can go more close to 20,000 RPM or 30,000 RPM. Again, it depends on the machine tools. You can set the high value for your spindle right in here. And this can be set. So if your programmed spindle RPM is higher than the high value, your posted code will use the high value to cap it to the high value in the posted code. So make sure that you update your post processor to reflect what's set on your machine, what the machine tool is capable of for your high and the low values. And also you can specify your spindle direction in here, which could be M3 or MO3 for clockwise and counterclockwise rotations. Now in turning, we also have the constant surface speed and constant rotational speed. Those codes can be set right in here for the spindle, and also for the feed rates you can specify the units per minute and units per revolution code as well for turning module, which is typically used on CNC lathes and turning centers. So folks, with this, I've given you an overview of the feeds and speeds settings in our CAM product. If you do have any questions, we'll be more than happy to answer them for you. And
today, just one other thing. There were some questions about the blog. I think most people are not familiar with the blog. Can you just motion on over to the blog and the two articles that I referenced in the question panels? Thank you.
Absolutely. So to access our blog, the easiest way for you guys, folks, to do it is go to VisualCam or RhinoCam or VisualCam for SolidWorks or LibreCam from the menu, and then click on website. So this will direct you to Mexsoft's website. And as you scroll all the way down to towards the bottom, the footer, you can click on Mexsoft blog, and it'll directly take you into our blog page. And as Joe pointed out, we have two recent articles. If you search under recent articles, you see that there's one about the milling feeds and speeds calculator, and you can read about it. And we also have another blog article on how to customize the material data for feeds and speeds. And this blog article have been put together by my colleague Don LaCourse. And you're welcome to read about it. And if you have any questions, please let us know. And again, to access the blog article, you can go to our website, mexsoft.com, and then select the blog link from the bottom of the page, and they should take you directly to the recent articles and the blog articles.